Hi and welcome to this lesson on calculations involving Gibbs-free energy. So in the last lesson we introduced Gibbs-free energy and we looked at the fact that it involves both the entropy values and enthalpy values, takes them together, and then we can use our Gibbs-free energy value to work out the feasibility of a reaction. So we learned that for a reaction to be feasible, the Gibbs-free energy or the change value has to be negative. So in this lesson, we're going to look at calculations involving these values and how we can use temperature to predict the feasibility, and also how we can use Gibbs-free energy to work out the equilibrium constant of a reversible reaction. For a reaction to take place, the Gibbs-free energy change needs to have a negative value. Temperature change can absolutely affect the feasibility of a reaction. So in order to predict the feasibility, there are two parts of the equation that are relevant to us. So we need to look at the two terms. So we've got the first term, which is the enthalpy change, and we've got the second term, which is our temperature times the overall entropy change. So we can make some statements. If we keep looking at this equation, and we can just imagine that we've got a value here minus another value, we can sort of infer and work out whether the Gibbs-free energy change is going to be positive or negative. So if a reaction is exothermic, so therefore we're going to have a negative first term, and the entropy change is a positive value, then the reaction is going to be feasible because we're going to end up with a negative value for G, because both the first and second terms are negative. But if we've got a negative first value, so our enthalpy change is negative and our entropy change is negative as well, remember a negative sign minus a minus means it's actually going to turn this into a plus effectively. So the feasibility of the reaction will really depend on temperature, because we could absolutely be getting a positive Gibbs-free energy value coming out of this. The lower the temperature, so the lower the value of T, the more likely it is that the positive value for the second term to be greater than the negative value of the first term. So then delta G, or our Gibbs-free energy change, would then be negative. So we need a very low temperature if we have an exothermic reaction with a negative entropy change in order for it to be feasible. If a reaction is endothermic, so we have a positive first value, and a positive entropy change, so a positive value minus another value, then the feasibility of the reaction depends on the temperature, because it depends on that second term. How large, what's the magnitude of that second term? Subtracting it from the positive term. That tells us whether we're going to go into a negative value for delta G or a positive value. So the higher the temperature, the more likely it is for that negative value for the second term to be greater than the positive value of the first term. So they subtract to give an overall negative value for entropy, for Gibbs-free energy. Therefore, the reaction would be more feasible. So we're looking for a higher temperature for reactions like this for them to happen. But then if we had an endothermic value, so a positive first term and a negative second term, a positive minus a minus means the reaction's definitely not ever going to be feasible, because that's going to be two values added together. We're definitely not going to be going to negative territory, so delta G could never be negative, and the reaction is not ever going to be feasible. Remember that in the Kelvin scale, temperature is always a positive value, so the sign of the second term is dependent on the sign of the entropy change. And be really careful with double negatives. So you saw there were a lot of double negatives involved because we were minusing a minus value, which then means that becomes just adding two values together. Here's what we've just talked about summarised into a table. Calculating the temperature for when a reaction is feasible. So we know that when we've got a Gibbs-free energy value of 0, the reaction is feasible. When the Gibbs-free energy is 0, this is the temperature at which the reaction is just feasible. So we can use that to create an equation. So if Gibbs-free energy is 0, that means that temperature is equal to the enthalpy change divided by the entropy change. Let's have a go at a calculation to put that into practice. Don't forget to convert your units of entropy from joules in entropy into kilojoules. So you're going to need to divide the joules number by 1,000 to convert it into kilojoules. We can use the Gibbs free energy value to also calculate the equilibrium constant K. Very useful. So the equilibrium constant, remember, of a reversible reaction is the ratio of the concentration of the products to the reactants. Reactions with a negative Gibbs free energy value, they have a large equilibrium constant, so the value of K is greater than 1. And conversely, with reactions with a positive Gibbs free energy value, we've got a small equilibrium constant, so the value is less than 1. Because remember, the reaction is not very feasible, so it's going to be on the reactant side. And we can create an equation to illustrate this relationship. So the Gibbs free energy is equal to minus RT ln K, or our equilibrium constant. And we can rearrange this equation to make K the subject, and that allows us to work out the equilibrium constant. Let's have a go at a question practicing that.